So previously we looked at differences in means and we were simulating our sampling distribution. Now we want to look at what the theory says that sampling distribution should be. And we've seen this distribution over and over again. On all these theory ones, we notice our distribution is bell-shaped and symmetric and is either the normal distribution or the t-distribution. The theory says that our sampling distribution of differences in means will be a t-distribution under the right conditions. So this t-distribution will nicely approximate our sampling distribution as long as from our two groups, our sample size is at least 20, and the samples aren't strongly skewed. So those are our validity conditions. So as long as we have big enough sample sizes from both groups, and notice it's the same when it was just a single mean, the condition was sample size 20. Now when it's two means, both samples have to be at least 20. And we don't want strong skewing in either one of those samples. There is an alternative, and that is if these sample sizes aren't big enough or the samples are strongly skewed, the other option would be if the population distribution is symmetric. Now, we tend not to emphasize that because typically we're not going to know a lot about that population distribution. So, so typically we're going to be looking at this 20s for both the sample sizes and not overly skewed in those samples. So the theory-based is just going to go off of the t-distribution from our data and compute the p-value that way. So let's go to the app and we'll look at that haircut and gender data we were looking at before. OK, so here we have our haircut price by gender data we were looking at before. And here it is separated out as two separate sets of data. Here it is stacked. Notice that we would not be able to, let's switch this over to count here, 13. We've got 13 values in here, and we're supposed to have at least 20 in each, right? Those were our validity conditions. But I really do want to use this data again. So let's assume that the population is symmetric, which was the other validity condition. That way we can stick with this same example and compare it to our simulation approach. So I have this stack data here. I'm going to copy it. And then I'm going to go to the theory-based inference. And we're looking at two means. I'm going to paste the data. Let's clear this out. I've got headers, and it's stacked, just like they're showing in this example, where you've got the group name in one category and the amounts in the other. So I'm going to paste into there. Should have, yeah, gender and price. We'll use that data. OK, so here is our sample information. We see those men prices and women prices. And here was our difference in our means. And so now with the theory-based, we'll do a test to see, is this really significantly larger than 0? Is this mean difference sufficiently large? And if we look, here's our null distribution. Remember what that represents. That represents that if there was no difference in the average price of men and women haircuts in the population, when you sampled of these sizes, you would get these sorts of mean differences. And ours is this blue line way out in the tail, so a very extreme value if it was really true that there was no difference. And notice the corresponding p-value, 0.0006, very small. It's a highly significant result. So we are very confident in saying that mu1 minus mu2 is greater than 0, or in other words, that the mean price of women's haircuts is larger than the mean price of men's haircuts. Also, remember the theory-based will give us confidence intervals. So not only can we conclude that women pay more on average for haircuts, that average difference in the population is somewhere between $13.63 and $50.79, at least at the 95% confidence level. We're 95% sure that the mean difference is somewhere in that interval. And remember, what you look for in a confidence interval when you're doing differences is you'd love this to be all positive or all negative, because that means that all the possible values in your confidence interval are indicating one mean is larger than the other. If this confidence interval straddles 0, that's bad news, because then you're not confident which one's the larger one. So we should expect this to come out all positive because we had such a strong p-value in our hypothesis test.